Hey, what's going on, everybody? My name's Kevin Rice. I'm a recent intern at Wolfram Research, and today I just wanted to bring to you the perspective of someone who has been using the language for a couple of years now. I'm a junior I just finished my junior year at Boston University, and I've been using the Wolfram language basically since I started at college. So I got a couple of few years under the belt, and I just wanted to take kind of that intermediate level knowledge and show you what we can do with it. There might be some missteps along the way, but that's life. And hopefully you can just learn from what we can do. And I've also got my friend Zach here.
Hi, my name, sorry. Hi, my name is Zach Shelton. I'm also a new intern at Wolfram. I have very little experience with Mathematica and Wolfram Desktop and the Wolfram language. I actually come from a physics background, so I've done most of my work in Linux and Python. I'm currently a graduate student of Florida Tech. I do a lot of work in high energy physics. So hopefully I can learn a lot more about Wolfram language. I know some now that I've been working for about 6 months and I've been able to experiment with it, but this is a good opportunity for me to kind of ask questions that maybe someone who has a background in another language or has done programming before to kind of ask those questions. So I'm very excited to get started.
Yeah, so let's just jump right in. I'm going to share my screen here. And what we thought that we would start off with is there's this great website called Rosetta Code. And what they have is kind of a large curated list of problems in computer science that can be on the difficult or easy side. There's a range of difficulties in there. But the great thing is they've broken up their website by language. So they have a website here with all the problems that haven't yet been solved using Mathematica. So what we wanted to get started with was we wrote some code up that would create a list of all of the different problems and the hyperlinks to them that haven't yet been solved with Mathematica, just pulling them right from this website. And you can see there's a lot of them. I'm going to go ahead and just collapse that down, and we can see how many of those links there are. So I stored them in this vector there. Looks like we've got 329 problems to work at. We're not going to get through all those. Don't worry. We're probably just going to look at a few of them. But we figured we would just grab a random one. So the way to do that in Mathematica would just be to say random choice of the links. You see it just gives us a random link. And just to speed things up here, I can use system open to have it open right in my web browser. And it looks like they want us to start with percolation mean cluster density. That sounds fun, right, Zach?
Yeah, we're gonna learn a little bit about, okay, we're gonna learn about neighborhoods. This is throwing back to like numerical analysis. Hopefully we can get through this. I'm excited.
Yeah, this one looks intense. So there's a lot of code, a lot of text up there, but we only care about the task. We'll read this if we have to. So show the effect of varying n. Oh, they probably defined that up there. Oh, it's an n by n square matrix. Cool. So varying the size of a matrix on the accuracy of simulating the mean cluster density um, for p, which is likely some sort of probability. Yep. So the probability of being a 1. Okay, so we've got some density as a function of the probability being 1/2. So it's an even density. You've got as many ones as you do zeros. Going up to matrices the size 1,000 by 1,000. That's a pretty big matrix. And okay. Oh, there's extra credit. That sounds good. All right.
Okay, all right.
Do you have any idea what we are even
Probably,
really starting off doing here?
so you probably want to produce a 2D matrices, a
Yeah.
Boolean matrices.
Okay.
Um,
Right. So it's a
so
matrix of n by n.
yeah, so what we need to do is we should create a matrix, an n by n matrix, where every value is randomly assigned, true or false, 1 or 0.
Right.
So, and we need to
So
have it be the probability of 0.5, which is just 1/2. It's a coin flip.
right. It's a fair, unbiased probability. So the first place that I start always with any sort of question is just going to the documentation, reference.wolfram.com if you're on the internet, or just under the help window here of your built-in Mathematica install. And the first thing that comes to mind is this function bool, which can give you ones and zeros based off true and false. But I'm not sure if that's going to be the most efficient way to generate a matrix of this kind.
So how do we have we can have a randomizer, right? There's probably like a
True.
probability thing. So like
True. We can maybe do like a random integer.
Yeah.
And with this, we can get an n by n array of pseudo-random integers on some range.
Well, we do
So
need to make sure that it's, I guess as random as it can be, but it's technically, I guess if it's 1 and 0, it will be 1/2 because there's only 2 options. Yes.
right.
So
Yeah.
I guess we can start with,
So here's like a 15 by 15 matrix. It's really hard to see in that form, but if we make, oops, I spelled matrix wrong. If we make it in matrix form, that's how we
wow.
humans look at that. So, okay, yeah, it looks like we've got a matrix of zeros and ones. So what I did was, okay, choose either a 0 or a 1, and it's pseudo-random, so it should have a bias of 0.5, like the problem calls for. And it's 15 by 15, perfect. We could bring that smaller so we could actually count the numbers. Yep, there's a 5 by 5, perfect.
Okay.
Yeah,
So now we
and
need to do something. Now we need to, so this is like, I guess we're trying to see the density of clusters of 1 or, ones.
right. So, okay. A cluster of ones is a group of ones connected vertically or horizontally using the von Neumann neighbor rule. Ooh, what is that? Brings you to a Wikipedia page. Okay.
good.
Oh, Cellular automata. If only we had Stephen here.
Okay, all right. So can we make a cellular automata with the von Neumann neighborhood rule?
Oh, that is a great
I don't
question.
know. I have no idea. I know you can make a bunch of them, but
There's gonna be a lot of stuff that shows up for von Neumann. He's done a lot.
Well, I guess
Ooh,
look at the cellular automation. Yeah, that's probably where we want to start. It probably is a
yeah.
rule. So if you go to details, we can pop out and see
Oh, yeah, yeah.
should be able to see every possible there, von Neumann. I don't know. I don't know what this is gonna do, so we can definitely test this, but I really don't have an idea.
It says it's a possibility for neighborhood. So that
Bernoulli
gets,
distribution, random variant. Ooh, that's a good idea. Can
oh, do
you?
we have something from the,
Yeah, do you want to run that? I'm just very curious what it does because I literally have no idea. So
yeah, it looks like we got a significant here.
you have to
Oh,
enter a
P.
number for P.
Yeah, P should probably be 0.5. Oh, and it looks like,
Can you get a matrix for that?
yeah, of
That should
course.
be very.
So it looks like this does about the same thing we had, except using a Bernoulli distribution.
It's probably
Oh,
more. It's probably more like correctly, like truly
mhm.
random, because we
Yeah,
needed
it's a
the
coin
one.
toss distribution.
That's
Right.
good. Thank
So,
you for
right, this
checking.
way we could also vary P then. If we wanted it to be extremely biased towards 0, we get a lot of zeros at a lower number. If we want to be extremely biased towards 1, we get a lot of ones. So that's a really neat way to change the value of that P there. That's great.
I feel like I've learned a bit there. I actually didn't know that, so mind
Yeah.
blown.
I wonder, I'm just going to make a quick manipulate out of this so that we can vary P on our own. Let's see if we have P going from 0 to 1. Just kind of what this matrix. So when we have P is 0, it's all zeros. P is 1, it's all ones. And in between, we get some randomly generated matrix where they're roughly equal at 1/2. Yeah, around 1/2.
Well, that's cool.
And more ones, less ones. So that's pretty neat. That's a great way that we can change the relative density of ones and zeros.
Okay.
Yeah, so just to recap for everyone who might be joining now, we're looking at some random problems from this Rosetta Code website, and we're just going to try to dive in and see what we can do with them. The first one that our random choice generated for us was this percolation mean cluster density function. And what we want to do is, it's a bit of a tough question. What we want to
I'm in the
do
middle.
is, oh, what was that?
I don't know. I'm sorry, Lucas. I don't know what you mean. But I will say, just to catch everyone up, we are trying to calculate the mean cluster density of a percolation matrix, or a percolation theory, I guess is what it is. But it's a randomly generated thing from 1 to 0. It's a coin flip. And we're just going to try to prove that as n approaches infinity, your numerical solution to that k function is 0.06577, some number approximating to that. So we're just trying to, I guess, solve numerically a, I guess, analytical solution. So that's kind of what we're going off of.
Yeah, I'm just a little curious as to how we're going to define this this K of P here, the mean cluster density.
So let's see what mean
Um,
cluster density is. Let me look it up.
oh,
You can,
yeah, is that a hyperlink? No, it's not.
I
So
mean,
yeah, mean cluster.
I'm sure
Well, actually,
someone
did
in
they
probably
define it?
knows.
Yeah.
Just did.
Uh,
Um,
well,
uh,
you had
you,
a great idea with using the actual cellular automata function.
yeah, so
I
this
wonder
is
if,
the von Neumann rule, right? So theoretically, and this is
uh-huh.
a cellular automata we looked up on Wikipedia and we're reading about this. This is a cellular automata. So theoretically, we should be able to
Oh, I see.
use the cellular automata function
Yeah,
to
it looks like,
recreate this.
from what
That's
I'm
the
reading
idea.
here is the cellular automata function would generate something using the von Neumann neighborhood,
Mm-hmm.
but basically we want to generate it, which we already know how to do, and then measure the neighborhood instead of using it to generate. Meaning, I think if we
Okay.
actually used this, it probably wouldn't be really random, if you know what I'm saying.
I guess that makes sense.
I guess that's true. Yeah.
I I
So,
I would say that's something I learned about with cellular automatas. I'd never like used or touched them. The closest thing I ever came to that was like random walks for like
mhm.
electrical, or I'm sorry, electric field calculations.
I'm wondering if we can use some sort of neighborhood function here to actually tell us which neighborhoods are containing ones and which aren't. So if we were to look at this right now, the number of clusters here is this one here, whoops, this one just in the upper right, this one composed of these ones, and this one down there. So we've got 4 clusters in this matrix. This one, it might look like there's more because there's more ones, but actually this whole guy down here up to there is a cluster. And then this is a cluster, and this is a cluster. So there's actually only 3 in this one.
So we need to count each individual cluster. So are ones that are diagonal to each other, they're 2 separate clusters, or are they one cluster?
Yeah, it looks like for something, for a cell like this one, its neighbors are only the ones that touch it left and
Okay.
right, up and down,
Okay.
not
So
a diagonal.
all right. So and there's a neighborhood function in Mathematica, and with
Yeah,
that,
how does that work?
I have you're asking the wrong guy, but hopefully we can figure this out.
There's definitely a way to do this using graph theory for sure. Which there's been a lot of new graph theory functionality added in 12.3. A lot of stuff with trees functions too. And it looks like we're getting a
Find,
suggestion here to use something called find clusters.
yeah, it's a little
Ah,
bit on the nose. Well,
that
okay,
a lot of functions are named like that. It's like, oh, why didn't I think of that, right?
just find cluster.
The name is what you probably
We
would have called it anyway,
That's a
if we
good
were smart enough.
idea, Sanku. We'll try it and see if it
Yeah,
does
let's see if
work.
we can,
We
what happens
might
if we
just
just
break
run it
it.
on this? Oh, I have it in matrix form, so it might not work super well.
You
I'm gonna,
wanna, yeah.
yeah, I'm just gonna create a new one in list form, and we'll
Thank you.
try to do find clusters on that guy.
I
It
don't.
looks like
It looks very nice. I have no idea.
it is
I
slightly different, isn't it? What does this
um.
look like in matrix form? I'm gonna have to.
Could we try to find a cluster on a row? because it looks like this works on rows.
Hmm.
So I mean, we
Oh,
could
you're
try
right.
testing it on like just a row. So just try to create like, I guess, a line. I don't know how you make. You just make whatever, or just
Yeah,
grab one of the
or
rows.
maybe this is what it was doing actually. Yeah, so you're right. Let's just do find clusters on one of these rows.
Wait,
Yeah.
what did it just make?
Oh, what I did was mapped it across the whole thing. So it did it on each row individually. So this is the result for the
So
first
one
row.
row. So this and those ones. Okay, no, that's not gonna work. Because right now, this first. Actually, I have no idea, to be honest.
Oh, found there's
I
all
just
one.
grouped
And
them
there's all the
together.
twos.
Oh, okay.
Yeah,
They're together.
this is
Uh,
good.
all right.
Um,
I'll look into some neighborhood stuff and see what's going on with that.
yeah, yeah. This is definitely something that the Wolfram language is built for. This type of graph theory, finding clusters and stuff like that.
Jeez.
I just personally have actually never really done much like this with finding clusters.
I mean, you want to try an adjacency graph? Adjacency
Oh,
graph.
how does
I
that work?
so we're supposed to give it. I guess it needs an adjacency matrix, but
Oh,
theoretically we
well,
should be
maybe
able
that's
to
what that
produce.
is.
Maybe we should be able to produce it. So I have no idea, but maybe
Yeah,
we could
let's try
pass it
doing
and
it
see
on
what
this
it
guy.
looks.
So adjacency matrix of this guy. Oh wait, we wanted graph, my bad. I did the wrong one. Adjacency graph. Whoa. Uh, that is a graph. That is definitely a graph.
I I don't have a math degree to explain what this means, but it looks
Maybe
very
the
cool. No,
number
I'm
of
just kidding.
nodes.
I think it's each node. I have no idea. I really don't really have a clue.
Hmm. Ooh, something called nearest someone has suggested.
Nearest
Let's
might
see
be
what that
a good
does.
idea. Probably.
The list of elements to which X is
That might be a good
nearest.
idea. This would be very on the nose if that's what we need, but it would be
Hmm.
pretty funny.
Or maybe nearest neighbor graph. See,
We could
I
try it.
use the see also section all the time. If I know that there's a function that is similar to what I want, like, oh, I want something that's near, let's try the nearest function. And then, oh, look, see also, we've got all these other functions that are similar. And probably what you're looking for is going to be in there. Ooh, let's go see what happens when we do this. Nearest neighbor graph of this. Huh. It's a three-dimensional graph, I think.
I think I have no idea what it just did, but that's cool.
Right. That's the
That's
thing.
that's very cool.
Oh,
Hmm.
so some
Yeah,
people are
we
just
could jump
wondering kind of what
back.
we're working on. Yeah. I haven't showed the question in a while, so that's my fault. There's this Rosetta Code website which has a lot of really cool problems on it. And the first random one that we pulled was this percolation mean cluster density. I honestly have no idea why this is interesting, but
I assume the problem's been solved analytically, and what
yeah, in
we're
fact,
trying to
I just
do
noticed.
is we're trying to solve it, numerically. So the idea is if we create, a random matrix of n by n size with exactly a probability of 0.5, and we count the number of clusters in there numerically, we should still approach uh, this limit that we get here that can be
Yeah,
determined, analytically, or I guess
in fact,
theorized
we
analytically. I have no idea.
on the Rosetta Code website, it links right to Wolfram Math World down here, which I should have noticed. Really cool. So there's a perfect example of our technology just kind of being used everywhere. But basically, it appears that this is some sort of function, and it follows this. This is the what does that stand for? Yeah, the Online Encyclopedia of Integer Sequences. So it follows some sequence. So we could cheat here. And just use this.
Can you grab an integer sequence?
Yeah, we can from Wolfram Alpha here. And if we wanted to, Here it is just as computable data. But yeah, basically this is some sequence here of, as you increase n, you're increasing the number of clusters that you have. I don't really see much here about how to calculate the number of those clusters.
Well, I think, well, okay, so we have clusters, but we're trying to also like create the cluster or try to count like the number of clusters because this corresponds, this is a sequence, right? But this also
Right.
corresponds to, you know, what's it called? Actually, this might help us. They say it's an isolated group of adjacent, horizontally or vertically connected. So we need to count the S clusters, and the S clusters, if you go back to the table we made or the matrix we made, I'm sorry.
Yeah.
We
Like
need
this guy
to
up here.
count the number of groups of ones that are connected vertically or horizontally. So this top one, there's five groups,
Uh,
right?
4 of them, right?
Four, I'm
1,
sorry, I
2,
can't
3.
count. Yeah,
Yeah,
four.
that's fine. That's fine. And
So if
well,
we,
that is a good question whether this one wraps around to the bottom there, but I don't think it
so
does.
C of n, so C of n in this K function is the number of clusters in a randomly constructed matrix that we have here,
Right.
which are Bernoulli distribution of 0.5 coin flip. And that's the number of clusters. So we need to count the number of clusters in our matrix. I think that would be good.
Mhm. I say we just go for the extra credit here, and we graphically show the clusters in a 15 by 15 grid,
Go
because
ahead.
we can
That,
create that grid pretty simply. So I'm bouncing back up to the top here, but okay, here's the grid. And the real question is just how do we create, how do we show those clusters? One way that could help us right off the bat is maybe just highlighting the ones so that they stand out, putting them in a different color. Let's see, maybe there's a way to do that in I'm gonna go to, instead of random integer, I'm gonna use random choice here. And we're gonna choose between a 0. What did I do? We're gonna choose between a 0 and a colored 1. Or let's just even choose between 0 and red. So all these red squares, those are the ones. Does that help you see it better, I think?
yeah, that's a good way of
Yeah.
looking at it.
So basically I've colored all the ones as red, which is RGB for 1. So that's kind of neat. This shows us, okay, there's actually a big cluster here. This is a different cluster, different cluster. The real question is, how can we count the different clusters in there? Do that. Maybe if we could look at each one and see its neighbors and whether they're.
There's a
Oh,
hint, and you could check
there's
that out
a.
because
We
more.
got a nice hint in the
My
chat here
mind is
of
being blown.
this function.
Anyway,
Oh, morphological components
that's
is
fun.
something that is pretty neat, where you can take something like, here is a black and white image, and it says, okay, all those different white things are clearly separated, so we can
Oh,
color
that's
each
cool.
one. Yeah, if we got rid of this
Try
colorize, probably give us
try
this.
feeding it. Try feeding that. It looks like you can just feed your matrix in.
Let's try it. So we've got this guy, and we want the morphological components of it. It's gonna be pretty big.
Try changing it back to ones, or just taking ones
Yeah,
instead.
that's a great idea. I'm gonna
I think this might
oops.
be the way to do it.
Just gonna generate a graph here and copy it down there.
Corner neighbors equals false. Okay, add the corner neighbors argument.
It looks like it's kind of expecting an image.
This
Um,
matrix is an image, or theoretically, you could just read the
eh,
matrix as an image, right?
that's a good point. Yeah, an image is just a matrix of hues,
We
right?
could just convert this to black and white too. Yeah, exactly. He knows.
I spelled something wrong there. Corner neighbors is false. What's the error that we're getting? Syntax error. Really happy about this guy. Is it? I'm going to convert this back into a list form. It's normal, really helpful function, converts everything to kind of the normal way that you see it. And it's still not pretty happy about that either.
Cannot be followed. Image. I have no idea. Try passing the image function, like image, the list
Convert
through
this to
an
an
image.
image.
Yes.
It's even still not too
Well,
happy.
okay.
I'm going to get rid of this option real quick. And I threw in an extra E
Imagey.
there. That's my fault. Imagey. It looks like it's kind of returning back. Oh, no, that's something different, isn't it?
Is it?
What happens
It
if we
looks
colorize that?
identical.
Whoa.
Colorize are original.
Mm-hmm.
That's
Oh,
kind of fun.
so if we take our original and colorize it. Oops. This is what it looked like.
Try passing the original function that you used to create it. Like you used to make the matrix and then put that in morphological component. It's a hint we got. So instead of passing it the long list
Uh-huh.
of, try making it in the function. One line.
Oh, so what you're saying is take this whole morphological components, create a
Yeah,
new
that's
guy right
perfect. Just
there,
like that. Yeah,
which
that's just,
I can evaluate this in line theoretically.
well, you have to
Oh,
close your,
we're missing some brackets there. So I'm gonna evaluate that in line. So that's what it gives us as the random matrix. And
go back and, or show it, don't colorize it, show it as a matrix.
yeah, I'm gonna, this guy?
Or no, just show it, show the resulting matrix, the matrix that morphological components makes as like numerical data. I think it's gonna give us what we want.
Like the
All right,
highest number in here would be
show it
the,
in matrix form. I gotta see it like in a matrix, 'cause
yeah.
I can't imagine things. Okay, show
Yeah,
us the morphological components.
okay, so basically I think what we've got going on here is, all right, so for everyone, let's get caught up here. We've been speaking kind of fast, but basically we've got this random matrix where it's filled with either ones or zeros. We can
Yeah.
show that colored, where these grayer things are 1, black is 0. And so this shows us really explicitly where the regions are. One region there, one region here, and one region down there.
Mm-hmm.
When we do this morphological components, which is this great function that takes something, breaks it up into its components, and then you can do something like colorizing
Can
them
you?
to really show where they are.
Yeah.
So when we do that on this matrix, whoopsies. Oh, hold on, I went too far back. So when we do something like that on this matrix and colorize it,
Can you put it?
what it
Can you also explain
does.
in matrix form?
Yeah, this is it in matrix form. This
Yeah.
is the
So
matrix
show
that
us
we're
the
working with.
morphological components in matrix forms, because
Right.
this is a matrix, right?
Yeah, exactly. So real
Yeesh.
quick, it's colored the different regions, right? This region's the same color. This
Yeah.
is a new one, and that's a new color. And in matrix form, those are going to show up as
So it labels, it counts them up.
1,
So
2, and 3. So if we just found the maximum number in there, right? We've got
yeah,
region 1, region 2, and region 3. The maximum number is there is the number of different regions.
morphological Euler. Can you try morphological Euler number?
Yeah, let's
I have,
try that.
this is some cool stuff, man. I
Well,
wouldn't have thought of
a lot
this.
of these functions, never heard of them. And that's the great thing about the Wolfram language is it's got such an extensive references, such long documentation for every single function.
Compute the
Um, the number of white
morphological.
objects. Oh, minus the number of holes.
I mean, we could
That's
try it.
that's
Let's
kind of
see.
neat.
Well, we know that this thing has 3 clusters based on our rules because no corner neighbors, it's got to be up or down, like the rules we had in the problem. So let's try passing the number, the Euler number, to this matrix
Hmm.
and see what it throws up.
Right. Pass it to this guy, this matrix that we
Yeah,
had.
yeah, try that.
Yeah, I'm not sure about this holes thing. Um,
Ouch.
oh, image or graphics, my bad. I'm just gonna do normal on that.
Image.
Or I got
Ah,
1. Yeah, and I
okay.
think that's probably because of the holes, right? It sees a hole here, and it says
Mm,
this isn't 1. So if this one
yeah.
doesn't have a hole, that's none.
Okay. All right
Um,
then. Well, I think for the most part we have like a working solution, right?
yeah, I think this works. We combine morphological components with the function that we use to generate the matrix. Sorry, I'm scrolling back up here so far, but this is
You
the matrix generator right here. If we throw that in, so this is a 15 by 15 and it has 16 different guys in it. And just to demonstrate that that's actually kind of working as intended, I'll just show this in matrix form. So we've got that bad guy there. Let's colorize it so that we can see what's going on. Wow, there's a lot of different regions there. But if we were to just do this morphological components of it, normal again, and colorize it instead, what we've gone ahead and done is
oh,
colored each of those regions. My screen isn't even big enough. I'm gonna drop that down. So,
that's cool.
yeah, we've taken all those individual regions and made them into different colors.
Okay.
Region, color, color.
So the
It's
last
pretty
step,
neat.
yeah, the last step is we gotta create, we have to numerically take
We
the limit of this.
we basically just did the extra credit. This is
Yeah, I
showing
mean,
the
it shouldn't
clusters in a
be,
15 by 15 grid right here.
I think it shouldn't be that hard for us to compute the average.
Yeah. Let's see. So what we want to take is
So the
mm,
task is to do it at least 1,000. So at least 1,000 by 1,000 matrix.
oh, okay. And what they're saying is as n goes to infinity,
Clusters over n squared, which is just the
the
area
number
or
of
the number
clusters,
of
which is the
elements.
max, divided by, and it should tend to this number here, 0.06577.
Yep.
Let's just do it for one of these guys. Sorry, I'm scrolling back up here again, but this is what we, no, this is what we used to make a 15 by 15. If we did that for 1,000 by
This is gonna
1,000,
print it.
I'm just gonna real quick use a with statement. So locally saving the variable n as 1,000, just so that we don't have to write numbers all over again. And I'm just gonna put max out front here so that we can divide by n squared is what we need to do, right? So
Yep.
this whole guy right here, that's Cn. That's what they call Cn, I believe.
Mhm.
And now we're dividing by n squared. And if we do this enough times, we should eventually get something that's 0.06557,
Well, we're getting
averaging
that.
over a bunch. We are getting right around there.
So can we iterate this series? Like, can we
Yeah,
do it
let's
from
make a
n
table
like
of them.
to 0 to, I don't know? Can we do something obnoxious like 10,000?
I did a bit of a hard computation here. I did the evaluation 1,000 times. And let's
Oh,
just find the average of that, which I believe is mean, right?
oh,
The
yeah,
function would be mean.
it's mean.
Yeah, the mean of a list gives the statistical. Yeah, okay. And the mean of that list,
Okay. So
pretty
we're
close. We only
We're
did
getting
100.
there. We're getting there.
Yeah,
And I mean, if we increase the size of n, this would get
right.
closer.
Yeah, for sure. So we could, for example, do a table. We can change n. Let's do
Mean around.
n going
Oh, that's
from
kind of cool. What does mean around
1,000
do?
to
After you're done, I just
1,400.
want to see what it does because I didn't know what mean around is.
Yeah, I'll get this generating. It's going to do a lot of processing. And we're being told there's a different function called mean around. Oh, neat. Okay, so this will tell you the mean and the uncertainty. Wow, that's really helpful. It's new in 12, so glad someone's paying attention. But
Experimental. We'll put it to the test. I actually would be very curious to see this once it's done. So
yeah, for sure. So basically what I've got going on here is we're calculating the value that they said to calculate for matrices of size 1,000 by 1,000 up to 14 by 14, 1,400 by 1,400. And we've got a list of all the different values of those. And we're going to pass that to the mean around function, and we get 0.066 plus or minus some really small numbers. So it looks like we're actually getting an average slightly above their approximate value there.
yeah, and that's a
Um,
series that's tending to infinity, and we just took
that's a
1,000 to
good point.
1,400. So like, I mean, how good? And technically, we're taking an average of like, we should really be taking like a series of this, not the average of all the values.
Right. Yeah, let's see. What if
If we
we
just,
do this for a really high value of n? How high do you want to go? 10,000?
I don't know what's it. I don't know. You might break the computer, so it's up to you.
We'll see.
I mean, we'll test it. I have
Yeah,
no
let's just
idea.
give it a shot. They are slowly adding progress reporting. And oh, look at that. We're
That's
getting
pretty good.
closer.
That's pretty good. I
Um,
mean,
let's try 5 times that much. So they're slowly adding a functionality of progress reporting so that computations that take a long time like this should be able to show you a progress bar. I think that's really neat. They've already added it for a lot of functions, especially in the visual video processing type of realm. So if you're doing some long video processing, you'll be able to see how long it's taken, maybe even what step the function's working on, and especially eventually how long it expects it will take.
that's cool.
So,
Hopefully this finishes. I
oh,
think
I'm sure it
it
will.
was good with 10 to the fourth, but once we went to 5 times 10 to the fourth, all bets are off. It
Yeah,
was too much.
let's see how we're running here. CPU is it's fine. It can handle it.
Okay.
Question is the
It'll
memory.
get there.
I'm maxing out on memory at this moment. Because
Well,
yeah,
if
it's
you
pretty
want to
memory
keep,
intensive to
if
make
you want
a
to let it run,
5.
you can.
I'll give it a few more seconds and then we'll probably end up killing this.
But that's cool though.
But in the
Can we,
meantime,
could you generate like a series from like 1 to 100 of
yeah.
I mean, obviously a 1 by 1 probably only have one or no clusters, but it'd be cool to see the series.
So it looks like someone asked us if we should be removing single points that aren't connected to anything.
No,
And
right?
I think that would technically be a cluster.
That
It
is, yeah, that's a
might be more of
cluster.
a cloister because there's no one connected to it. But yeah, if you have a 1 that's surrounded by zeros, that's technically a cluster of 1s
Yeah,
by this definition here.
yeah.
Um,
At least that's what we are interpreting. I mean, theoretically, and I mean, it is
there could be
doing what
another
we
interpretation.
expect. It is doing what we expect it to do. It's tending to, what's it called? You might just want to stop it.
I'm gonna have to kill this. Yeah, sorry about that, guys. We bit
But
off more than we could chew.
it
Flew
is
too close to the
tending,
sun.
it is tending to, oof, oof. We're gonna have to leave the whole kernel behind. It is tending
That's fine.
to, it is tending to, the 6.5,
Yeah,
0.065. So it's,
we got really close when we went 10 to the 4. I'll just do 10 to the 4 again. Because that didn't take too long. Hold on,
and
everyone. Looks like killing my kernel was, there we go. So I'm gonna get that running, and I'm also just gonna, in case we want to do another problem, get all this loaded up again because I killed the kernel, so it's gone. That's my bad. So yeah, it looks like while I was away, we got again really close to 6.5 there. So I think this is proved. We did it.
Yeah, so I guess going off of this, a cluster is one surrounded by zeros, but two ones that are one above and one below, that is one cluster. And a cluster of two, and if you have two ones that are diagonally adjacent, that is two clusters. Because the von Neumann neighborhood rule means that the ones that are connected have to be either above or next to each other or below. So
Yep. Yeah,
following the
that all
rules,
sounds right to me. Yeah.
we got there. I think that's pretty
All
cool.
right. Cool. Well, let's call that one solved. I say we just look at one other and see if it's doable or not in the time that we have remaining.
We can at least, great, prime numbers. I like
Prime
prime numbers.
conspiracy.
I like prime.
Prime numbers are great.
I've never worked with them, so we hopefully will learn something, or at least I will.
Yeah. This all right. I'm not gonna lie. I've actually already looked at this one. So
Is this like one line or something where it's just like,
this is not terrible in mathematics. I'm surprised I didn't put the solution up there.
so
But
considering, wait, what is it? So considering
so
the,
yeah, there's this weird like quotes from people that there's some conspiracy that so basically prime numbers should behave like random numbers. Cool. And there's some conspiracy that this is annoying. I'm gonna get a little wider. So prime numbers have decided to have preferences about the final digits of their primes that immediately follow them, meaning that they're claiming that there's some sort of conspiracy in that if you have a prime number that ends in 3, the next prime number is more likely to end in 9. Okay. I mean, to me, that sounds kind of common sense, right? For example, if you have a prime number that ends in 2, the next prime number has to end in 5 because there's only one prime number that ends in 2. It's 2. Same with 5, actually. The only prime number that ends in, or sorry, 2 goes to 3, I should have said. And then 5 is going to go to 7. That's the only one. So,
all
of
right,
course, there's going to
interesting.
be, right,
So
there's going to be patterns like that.
I'm sensing that we need to do, are we going to use associations for this, or are we just going to make a list and we can just count the one next to it?
Yeah, so
I have no
first
idea
off,
though.
I'm just going to,
You can lead
this
on
is a
this
list
one.
of the first 100 primes. And what I want to do first is the conspiracy is only between the last digits. So we want to reduce this list to just the last digits. So it
Oh,
should be 2, 3, 5, 7, 11.
do we just take the
13.
last of, can
Yeah,
you just take
so
the last of
something.
these? What does that do?
Well, we couldn't just take the last because a number in Mathematica is atomic. And what that means is you can't really split it up further, right? Just like an atom, it can't be
So-
broken up farther.
So could we take
But
their
if
string? Is that where we should go with it?
that, or what my thought would be is to break it into its digits. And I'm going to go to the documentation because you should always just start there. But
Are you mapping it, or like do you have to map this in order to do it? Because it looks like it combined it into one list.
Yeah, so what I'm looking for is the function that takes some integer and breaks it into a list of its digits. It's called integer digits. That's my fault. And what it did was, okay, great. We've got a list of the digits of each of the first 100 primes. So first prime is 2. That's easy. The number 11 got broken up into 1, 1.
So we just
and all we care about is the last of those, right? Yeah. So exactly. We just take the last, and what I'm using here is the map operator. And basically what's going on is, all right, let's look at these first 100 primes. And so this is a list, right? A list of size 100. If I were to just do integer digits of that, this might work. It depends on if it automatically threads. Oh, it does work actually. But for some functions, so for example, if I were to just do last instead of mapping it, it would just grab this list 541 here. But when you map, it applies the function to every single value in there. So if I pull up the documentation, basically mapping f across a list gives you the function f applied to every single value in that list, which is what I want. So I want the last function, which gives us the last element, applied to every single one of those lists.
So this is the last element of, or this is the last digit of every number. And so just so I'm clear, mapping is equivalent to like a for loop, but it's a little less. It's a little less like an iteration over a list. It's more of you're in parallel
because
applying a function.
Say in Python, right? If you had a list that just had some numbers in it, if you wanted to apply a function to every single one of those numbers, you would have to do, this is kind of pseudocode, but you'd have to do something like for num in, I forgot to say, list. So for number in list, give us f of num, something like that, right?
It would be not like, well, it would be a little like that, but you would have to have a for loop and iterate. So I go, okay, I kind of get where we're going with it. Okay.
Like I said, this is kind of pseudocode, but
we can not get off topic then, I guess. I just wanted to check in because I'm still confused by map and I've been like using it and sometimes I still misuse it. So
yeah, no, it's basically like what you said, where in Python you would do a for loop or do some sort of loop across every value in a list and then apply a function to it. Here we can just apply this function last to every value in the list individually and then group them together as a list.
Can we get 10,000 of them?
Sure, we could do whatever we want. So
number digit
10 to the fourth,
230.
really quick. And you see there's a lot of 9s, 7s, and 1s, and that makes sense, right? A prime other than 2 and 5 has to end in an odd number that's not 5. So there is going to be some quote unquote conspiracy going on there. Okay, so I'm just going to keep this small just so it's easy to read, but eventually we'll make it bigger.
I guess someone said, or someone pointed out in the chat, if you type number digit.
So this is a new function, I believe, in 12.3. I hope everyone has updated 12.3. Yeah. This came from the function repository. So someone had submitted this function and it was a great idea. So we integrated it into the language, which is really neat.
I guess if you have number digit and then 0, or your number, like your number, whatever, 1, 2, 3, as an example, and then 0.
Right, so this gives us the digit corresponding to 10 to the 0, which is 4. Yeah, that makes sense.
You can do this for decimals by going in the negative direction. That's pretty cool though.
Yeah.
Okay.
So I wonder if this threads across lists, like if I did 12 and 34, would it give me 2, 4? Cool. So yeah, this is a great idea. Instead of using last integer digits, we can just use number digit of the 0, and that should give us the same list. Perfect.
Oh, that's cool.
Yeah, so here's a great example of someone, thought this would be a great addition to the language and just went out and added it to the function repository, which I should have. Sorry, spelled it wrong. But
do you mind zooming in more on the notebook? Because I think people just have reading it.
Yeah, that's
can we get it? Yeah.
That'll work. Yeah.
Oh. Yeah, I have some experience with, someone's talking about Python and the mapping. I have some experience with the mapping stuff in Python in the past, but I don't like to use it just because I've broken it.
In case anyone's wondering what I was doing here, this is a Python inline cell. So if I wanted to execute Python code, I could in a notebook, in a Mathematica notebook. So obviously that's the most boring calculation you could do, but yeah, it gave me 4 and it computed it in Python instead of in Mathematica.
That's cool.
Oh yeah, so the punchline with this was just if anyone ever has a great addition to the language, anyone can add to this Wolfram function repository and anyone can pull from it. For example, there's a function that gives you graphics of playing cards. And if these functions work well enough and are helpful enough, eventually they might get added to the language. So here's the it has to download it from the cloud, but that's to be expected. And great, there's a playing card from the resource function. That's really neat, I think. All right, so we've got this list, and the alleged conspiracy is that the nth digit determines the n plus 1th digit. So what I want to break this up into is new lists that are n comma n plus 1. And the way that I first want to do that is using the partition function, because this breaks lists up into non-overlapping subsets. So if I were to partition this guy into lengths of list 2, and we're going to use an offset, it's either going to be 1 or -1. Oh, it's 1. Okay. So great. We've got 2 leads to 3. 3 leads to 5. So the structure we've built here is the last digit of a prime number and the last digit of the next prime number after it. What we can do from this is turn it.
Do you need to make a second partition or subset of? Oh wait, never mind. Wait, never mind. Bad question. You already did that. I was thought each subset was not connected to the other, but they are.
Oh yeah. So we've got 2 going to 3, and then we've also got 3 going to 5. Is that what you mean?
Ah, I see. Yeah.
Yeah, so that's what this offset of 1 did. If I didn't have that there, then you're right. It would be 2 going to 3 and then 5 going to 7, which is correct, but we're skipping that 3 going to 5 there.
I see. Very cool.
So building that back in gives us it gives us the full list basically. And what we want to change this to is, instead of 2 comma 3, we want it to look like 2 going to 3. And I'm obviously not going to do that manually, but I'm just going to try something here and see if it works. No, it didn't work.
Probably want to. You can use an association thread. It's probably what you want to use. Oh, or just do that. I don't even.
Yeah, this worked. Kind of. So I'm using apply on the first level here. This is a bit complicated, but basically what's going on is it's taking rule, which is this function that basically is left-hand side points to right-hand side. It has a built-in meaning. For right now, we're not really using that meaning. We honestly just kind of want arrows. But what it's doing is it's taking that list that had said 2 comma 3, and now it says, okay, structure that is 2 arrow 3, 2 pointing to 3. And the next step then,
do we just count?
Prime conspiracy. Yeah, we just want to break these up into bins. So we want to see how many times does 3 point to 7. There should be something like counts or
counts is what you want to use. It's counts. It'll give you what's right. I was actually just testing it on my own notebook. So if you use counts, it's gonna give you every time that association occurs of like 1 to 7, 7 to 3, 9 to 7, all that.
Oh, cool. So 2 is followed by 3 one time. That makes sense. And now we can beef this up. Let's do 100,000 different primes.
I think
so it's 100,000 total
wants us to do
numbers.
10,000 is what Rosetta
Code
wants. That's what Rosetta
Code
wants. But we did more, so there you go.
Well, this way we can compare it with the results too. So that's a great idea. And let's see, maybe if I just break this into a column, will that work? No.
It's in a column. It's just.
Oh, I see. It's giving us an association. What if I make that into a list?
Well, now you have no idea what any of them are. So you might want to keep it as an association, just because now we can see what they are. I actually don't know if anyone knows how to like print this nice. It'd be kind of cool to see. So.
And it looks like they've sorted it. Let's see if we can sort that so that we get
the most or the least to the most.
Yeah, so with the ones that show up once.
Bar chart.
Oh, that's a great idea. Someone suggested that we use a bar chart on this.
We could use a bar chart. Yeah, just add a chart labels automatic at the end of your bar chart. Or I don't know how you I don't know how you would do it inline, but chart labels automatic.
Great idea. Oh,
And then
cool.
I would just make your image or you make your graph larger. You can do that. Yeah, it works.
I'm just gonna manually do it. Yeah. Okay, so it looks like there is kind of a pattern here, like they're alleging in the conspiracy, um, in that it's more likely that, a 3 goes to a 9 or that a 9 goes to 11 than something like a 3 going to a 3 or a 7 going to a 7. So there you have it. That's the prime conspiracy. Do you think there's
So,
much more to say about this, Zach?
I mean, you could just like iterate it for like a big, very big number and then kind of just leave it at that. This just
Right.
seems like
Yeah, so
how
here,
prime numbers work, so I don't really know.
right. So I've bumped it up to 100,000 prime numbers, and it looks like that general shape held. So it seems to be there is some conspiracy there.
Yeah.
Um,
Well, it's so the extra credit is doing it for 100 million primes. So
oh,
can we do that? Is that 10
oh,
to
like
the
100 million?
8th? I
Uh,
would just type
that
in
might
like,
take forever.
okay, well, we don't have
Let's see.
to do that. We'll
The
end with
question
this.
about this is using memory.
If it doesn't work,
Mhm.
we'll just leave it at that and we'll just say have a good day everyone because we're hitting an hour.
That's a good point. Yeah. Basically, what we've done here is vectorized it. So we're working with a massive vector that has 100
Mm-hmm.
million prime numbers stored in it. That's going to be
Mm-hmm.
really memory intensive, but efficient
Isn't
on the CPU in general. If we were
okay,
to
so
do
it's
it in
very
some
memory
way,
intensive, but very
yeah,
efficient.
yeah,
Oh,
more efficient
CPU.
than
CPU efficient.
right. So you can see my CPU's having a fun time. The memory's getting up there, but it's actually doing fine. So this might finish.
Okay.
Um, we'll give it a couple more seconds before we wrap up. And I would say, just to summarize some of the cool things we talked about, we spent a long time working on this percolation thing. We, at the beginning, I would say, I don't want to speak for you, but I would say we really had no idea how to do that, right, Zach?
Yeah, I didn't know
How to do
percolation,
this problem.
what this was or anything about it, but we did learn a lot about the image.
Right.
I mean, how to work with these matrices and images, and some of the
Yeah,
functionality. We can apply like the image searching stuff to other images. So theoretically,
exactly. I would say what really stumped me at for this problem, okay, generating the matrix we figured out pretty quickly, but trying to break this up into clusters, using different functions and stuff like that, you can tell we tried a lot of stuff and we were pretty confused for a while. But eventually, with the help of others, we found a really neat way called morphological components. Who would have thought to break something like this up into different, essentially, clusters? So there's always going to be a way. And it usually turns out that in Mathematica, that way is super easy. Like, oh, there's a built in function that does that. In other languages, that way might be, well, let's look at every individual element, count up as neighbors, and, assign them to different lists and have 9,000 for loops, which isn't always the most fun to do. But eventually we got the answer, which I was pretty astounded by, honestly. But yeah, we did it. And we did this prime number 2. This one wasn't as difficult, but basically it just comes down to being able to find that perfect built-in function. So
when we learned about a
being
new
able to,
function in 12.3, that was pretty helpful.
yeah, yeah, new stuff in
Um,
12.3, always new functions being added. There was something like one new function added per day on average between these releases. That's incredible.
cool.
I would say
Well,
my takeaway is just to use the functions in this C also. Just see what's related to what you're doing and see what's something cool that you can come up with. And yeah, if
okay.
this finishes running and it looks similar, hopefully we'll put that out somewhere. But besides that, I hope everyone has a great day. I think we all learned something, Isaac.
Yeah, thanks for coming. Probably we may put these on Rosetta Code later. So if you have a better idea or a better solution, let us
True.
know. Um, there's some interesting stuff about primes. Actually, Gregory in the chat is talking about prime heads, how they randomize after a while, and honestly, I didn't know that. So
Oh,
very cool. Thank you very much for being involved, and thanks for everyone else that helped us and got involved.
yeah, we've had a lot of help along the way. That's been great.
Thank you.